Young scientists. Today we're here reviewing the Doppler method, the wobble method, the radial velocity method. All names for basically the same technique to find exoplanets. This method was predominantly used in the mid-90s into the 2000s. Today it's used in conjunction with other methods like the transit method. It's a reliable method, but it has a little bit of bias, and that's what we'll talk about a little bit later on in this. So what does this method rely on? Well, it relies back on common center of mass. If you remember, Isaac Newton said that objects don't just orbit the sun, they cause the sun to orbit as well. So these objects orbit in their common center of mass. So the star wobbles. That's why it gets the name wobble method. How do we detect that wobble? Well, we detect it with the Doppler effect. That's why it's sometimes called the Doppler method. And basically the Doppler method is a way of looking at the light of that star. When the star is moving at you, those light waves are getting compressed, they're getting smaller, they're getting tighter. And that's going to appear towards the bluer end of the electromagnetic spectrum. It's going to appear bluer. Our eyes aren't sensitive enough to see these things, but if we could move near the speed of light and we had sensitive enough eyes, you'd actually see the universe get blue shifted as we sped towards it. Now likewise, when an object that is emitting light gets away from you, what happens is the wavelengths of light get stretched out like a slinky. And this stretching out causes the wavelengths to appear more redder. They'll appear what we call red-shifted because the object is moving away. And what we can use is we can use telescopes not to see the planets, but we can see the subtle shift in the variation of starlight caused by the sun or star orbiting its common center of mass. When that star is moving towards us, it's blue shifted. When it's moving away from us, it's red shifted. And the greater the Doppler effect, the greater the wobble, the more you see this blue shift and this red shift. So what I've shown you here in a little bit of a drawing is just, we got a star and we got a planet, and this star is orbiting around the common center of mass, and of course the planet as well is orbiting around the common center of mass. When the planet is at this part of its orbit, you'll notice that the star is actually closest to us. So if you could imagine like Earth being in this general direction, kind of looking towards this star and planetary system. As the planet goes around, here's its position at time 2, the star will move reflexively over to this side. There's the star's position at time 2. Now the planet is moving towards us at this point. And as it's moving towards us, at point 3, it's not even moving at us anymore because it's kind of moving side to side. So we don't detect a Doppler shift at that point. I'll show you what that looks like on the graphs. Our star has now moved as far away from us as it could have. Now that planet's going to continue swinging around, moving away from Earth. And our star is now going to start moving towards Earth. And we're going to start seeing a blue shift because that light is moving towards us. The light is being compressed. And we can show this in graphs. So this type of motion is called reflexive motion. As the planet moves towards you, the star moves away from you. And as that planet moves away from you, the star moves towards you. And you're going to see that in the graph. And that can be something that's a little bit tricky. Now the graph I have here is a graph of the wavelengths of light. And you'll notice it has a positive signature and it has a negative signature. Some words that you're going to want to know for this. The height is called amplitude. That's basically how blue shifted or how red shifted is it. The greater the blue shift, the greater the red shift, the more the wobble. That means that planet has to be tugging pretty hard on its star to get it to wobble more. And the period, basically it's the time when the planet goes around the star once, or the star completes a full orbit. I've picked from here to here, where it returns back to that original position, as my period. But you could have done from here to here as your period. Again, it's just getting back to that original starting position. And on the simulation that we do in class, I believe it actually tells you the period. It can actually, I think it actually even gives you the number, or you can calculate it if you really want to go that way. You'll notice up here this positive signature means the light waves have been stretched out. And when they're stretched out, is that red shifted or blue shifted? If you said red shifted, you're right. So the top of the graph, this area of the graph, is when the star is red shifted. And when the star is red shifted, that means the star is moving away from us. It's moving away from us. Now you may ask yourself, Mr. Killiton, what is the planet doing? Hashtag reflexive motion. If the star is moving away from us, the planet must be moving at us at this point. Down here, you probably guessed it, the wavelengths are compressed, and you're observing a blue shift, and that means the star is moving towards us, and the planet is moving away from us. If we really wanted to graph this and take a look at how it relates to the little chart that I've done here, think about it. At time 2 for the star, this is when the star is moving the strongest away from us, the fastest away from us. This would be time 2. By the time it gets over here, it's not moving away from us. It's not moving towards us, so we don't see a Doppler shift. So time 3 could best be represented by this. By time 4, the star again is moving at Earth. So we see a blue shift. And by time 3, it's moving kind of to the side of Earth. So we're not seeing a shift at all. You could say that time... What did I do here? Oh, excuse me. I had the original starting position here. Time 1 being right there. What you'll probably notice is that the higher the amplitude, the larger the mass. The closer the planet is to the star, the tighter that period is, the smaller that period is. Remember, when we started doing Kepler's laws, the period of the planet is related to the distance from the planet. So if we know the period, we can tell the distance. And by looking at the amplitude, you can tell the mass of the planet, because that planet is causing its star to gravitationally wobble. A couple problems with this method. This method is biased towards large planets. Why? Well, because large planets are going to be easier to detect. If you're a large planet, you're going to cause that star to wobble more. It also doesn't work for systems that are not oriented directly at us or away from us. If it's tilted, some of that wobbling motion is coming at us and some of that wobbling motion is just kind of going in the down direction. So we detect a lower mass than that planet really is. So I may tell you a planet is 4 masses to Jupiter. That's the minimum mass that planet could be. That's the minimum size for that planet, which is really kind of a problem when you start trying to ask, well, could there be life on this planet? The other problem is if you have a system that isn't, if the system's oriented like this, where you have your star and you have your planet going around it and it's causing that star to wobble back and forth like this, yeah, we're getting a Doppler effect right now. My fist comes towards my cell phone, away from my cell phone, towards my cell phone, away from my cell phone. But if the system is oriented like this, where the planet's going around like this, my star's wobbling up it's wobbling down, it's wobbling right, and it's wobbling left. It's never wobbling at the phone. The phone would never detect a red shift or blue shift because it never moves in that direction towards the phone. So using this method, you look at a system oriented like this, you say there's no planets there. Here you say, best case scenario, this is like exactly what we're looking for. This is no planets, and if the orbit is inclined, then you're going to detect a planet probably, but the mass is going to be the minimum mass of the planet. It can't estimate what the real mass of the planet, and sometimes we just don't know, and that would eventually, we'd have to rely on things like the transit method and direct imaging. We can talk a lot more about that. So that was the review of radial velocity, the wobble method, or the Doppler method. And we'll talk about a few more methods in class, and I hope this has been helpful.